Out past the orbit of the planets, there is a giant invisible shield that helps make life possible here on Earth. This is the heliosphere.
Solar system is surrounded by a protective bubble that is created by the solar wind, a constant stream of particles that is being released by the sun's atmosphere and is blowing constantly outwards and protects us from harsh galactic radiation.
The heliosphere is always around us, but it's constantly changing. That's because the sun's activity changes on a natural 11-year cycle, as well as with shorter-term variations. As the solar wind fluctuates, the heliosphere responds. Around 11 billion miles from Earth to its closest edge, the boundary of the heliosphere is hard to study. Despite its importance to life on Earth, only a couple of spacecraft have flown through its boundaries, and comprehensive measurements of the entire heliosphere are limited. But that's changing with NASA's Interstellar Mapping and Acceleration Probe mission, or IMAP. As a modern-day celestial cartographer, IMAP will fill in the blank spots on the map of the heliosphere and help us understand the fundamental processes happening across our solar system. Spacecraft will be stationed at Lagrange Point 1, or L1, a location approximately 1 million miles from Earth toward the Sun. From that vantage point, IMAP will study our heliosphere in 3 main ways. First, IMAP will map the boundary of the heliosphere using special atomic messengers known as energetic neutral atoms, or ENAs. These largely start as normal, electrically charged solar wind particles traveling out from the sun. Like all charged particles, these solar wind particles spiral around magnetic field lines in space, like a roller coaster on a track. Eventually, the particles reach the boundary of the heliosphere, where they crash into others from interstellar space. When they collide, they become neutral, meaning they no longer have an electrical charge, and transform into ENAs. As a result, the particles are no longer bound by magnetic fields. This allows them to move in straight lines. Second, IMAP will measure tiny particles within the heliosphere, including some from interstellar dust, the leftovers of supernova explosions. Studying these interstellar particles will give us a better understanding of the material floating between stars and give clues about our solar system's infancy. Third, IMAP will measure the source of the heliosphere, the solar wind, in real time. High-energy particles from the sun can produce hazardous conditions for satellites and astronauts, as well as power grids and infrastructure on Earth. Measurements from IMAP will help us better prepare for dangerous solar particles and radiation that are headed toward our planet.